Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on these topics or are learning them for the first time, you're in the right place. Today we're continuing with functions and limits, looking at logarithms, exponentials and hyperbolic functions. So if you're ready to learn, then let's get into it. We'll start with the logarithm or natural logarithm here, which is represented by ln of x or ln x. The reason it's ln of x is because of the Latin logarithmus naturalis, which is the natural logarithm. And this is basically the logarithm of x base e, where e is a constant used throughout physics and it will be very important. We'll see it more with the exponentials and you'll see it going forward a lot. And natural logarithm of x can be defined as the integral between 1 and x of 1 over t dt, where t is this dummy variable which, when we integrate it, will be substituted by x. So as you can see, this plot is representing f of t, which equals 1 over t. So it's just a 1 over t plot, and the integral, this shaded area underneath the plot, is what our natural logarithm is defined as, so between 1 and x. From the integral, we can see that if we differentiate the natural logarithm of x, so d by dx of ln x, we will get 1 over x. And it also follows from the plot that if we are finding the natural logarithm of just 1, this is the same as saying the integral from 1 to 1 of 1 over t dt, which it will always be 0 because of the limits of the integral being the same. Now we'll derive this formula here, where ln of x1 times x2 equals ln of x1 plus ln of x2. So if we just start with ln of x1, we can write that in integral form as 1 to x1 of 1 over t dt. If we now define this variable s to equal x2 times t, it gives us ds equaling x2 dt. x2 is just a constant number. And we can rearrange this to say t equals s over x2 and dt equals ds over x2. So if we substitute these values in to our integral, we get, so when t is 1, if we look at this formula here, we'll see that s must be x2, and when t is x1, s must be x1, x2. And then 1 over t will become x2 over s, and dt becomes ds over x2. So we can cancel out these x2s, and we can split up the integral into two integrals, where we can write the integral from 1 to x1, x2, 1 over s ds, minus the integral from 1 to x2, 1 over s ds. And these are the same as saying, they're clearly just the formula, the definition that we have for natural logarithm. So this must be ln of x1, x2 minus ln of x2. So if we rearrange this, we have ln of x1, x2 equaling ln of x1 plus ln of x2. And there we've derived the formula we wanted to. We can work out some useful properties from this equation. So if we look at the natural logarithm of 1 over x plus ln of x, that's the same as saying ln of 1 over x times x, which equals ln of 1, which we know is 0. And so that would mean that ln of 1 over x equals minus ln of x. If we look at another example, you might see where I'm going with this. So ln of x squared is the same as saying ln of x times x, which would then become ln of x plus ln of x, i.e. 2 ln of x. And to write this generally, we get the natural logarithm of x to the n becomes n times the natural logarithm of x. Whatever the x is raised to the power of becomes the prefix of just ln x. It's a very useful property of natural logarithms. I just thought that I should plot ln of x to help you visualize it here on the right. So as x tends to 0, our y equaling ln of x tends to minus infinity, whereas when x tends to infinity, our y ln of x tends to plus infinity, but with vanishing slope. So it will keep bending over to a smaller and smaller gradient, but it will still tend to infinity. Now let's think about the exponential function. So if we just consider x equaling ln y, what is the inverse function of this? So y equaling f of x, where f is this undiscovered inverse function of the natural logarithm. To start with, let's consider where x1 equals ln y1, x2 equals ln y2, and then we'd have y1 equaling f of x1 and y2 equaling f of x2, these inverse functions. And if we just think about what x1 plus x2 would equal, we could write it as ln y1 plus ln y2, which, as we know before, is the same as the natural logarithm of y1 times y2. Now if we take the inverse function of this, we can say y1, y2 equals the inverse function of x1 plus x2. However, we also know that y1 plus y2, looking at just these, must be f of x1 times f of x2. This implies that f of x must be of the form a to the x, because that's the only type of function that can satisfy this, so let's write it, f of x is of the form a to the x, because when a to the x1 plus x2 is calculated, we know a to the x1 times a to the x2, that is the same thing, and that's the same as these lines here, so it must be of the form a to the x. Now if we think about our x equals ln y, when we differentiate this in terms of y, so dx by dy, we get 1 over y. And if we rearrange this, we can see dy by dx equals y. And this is an important result. We're basically saying that when we differentiate by x of our inverse function, so y or f of x, which we know is of the form a to the x, this is equal to itself a to the x. And there's only one number that satisfies this result, where we're trying to find a, and it's e. So a equals e, which equals 2.7182, etc. And it's an irrational number. And we'll see later in this course where it comes from. But this e to the x is this inverse function we've been trying to find for ln x. So is the inverse of ln x. And that's why we have the logarithm being of base e. That's where this e comes from. Here are two plots representing this exponential function. So on the left we have y equals e to the x, and it's this increasing function, and it goes to infinity faster than any other power of x. And on the opposite side we have e to the minus x, where it's going down, tending to the x-axis. And these are very common plots that you'll see throughout physics. Lots of different phenomena require an exponential function to explain, so you'll see these crop up a lot. So it's very useful to know what these plots look like and how to draw them. Now we'll discuss the hyperbolic functions, and clearly these look familiar to the trigonometric functions, and they are related via the complex numbers, which is something we'll look at in a later video. But for now, all you need to know is the definition of these and what they might look like. So for the first one, sinh x, which can also be pronounced shine x, it's up to you, but I'll be calling it sinh x, is defined as e to the x minus e to the minus x, all divided by 2. And it looks sort of similar to a tan x graph. And at the origin here, the gradient is equal to 1. And as the modulus of x approaches infinity, so in the positive x direction and negative x direction, the behavior of the graph becomes exponential. And that's the same case for cosh x, and there isn't really another pronunciation of that. I think everyone agrees on cosh x, and it's defined as e to the x plus e to the minus x, all divided by 2. And this looks like sort of similar to a quadratic, where it crosses the y-axis at 1, and this is clearly an even function. I forgot to mention that shine x or sinh x is an odd function. And we can see again that as x approaches infinity in the positive and negative direction, the behavior of cosh x tends to exponential. And then finally, we have tanh x, or some people pronounce it fan x. This is defined as shine x, or sinh x, over cosh x, which equals e to the x minus e to the minus x over e to the x plus e to the minus x. And if you times everything by e to the x, you'll get e to the 2x minus 1 over e to the 2x plus 1, and you will see these forms crop up. And this looks like it tends to boundaries at 1 and minus 1. As x approaches infinity, in the positive direction, tanh x approaches plus 1, and the negative direction approaches minus 1, and this, again, is an odd function. Other ways which they are similar to the trigonometric functions, apart from just the naming convention, is, for example, we know that sine squared x plus cos squared x always equals 1. Well, here we have instead cosh squared x minus sinh squared x always equals 1. We can also see some other identities, so sinh of x1 plus x2 always equals sinh x1 cosh x2 plus cosh x1 sinh x2. And that's very similar to the sign of x1 plus x2. Just get rid of all the h's. However, when we look at cosh of x1 plus x2, this is always equal to cosh x1 cosh x2 plus sinh x1 sinh x2. And this plus sign here is what differs from the cos x1 x2 identity, and the reason for that is the way that these hyperbolic functions relate to the trigonometric functions, and there's imaginary numbers, there's i's involved, and they would basically become an I sine x1 here times I sine x2 here, and these i's will then become minus 1 and therefore get a negative sign there. So that's how they differ. And then if we go on to differentiating them, d by dx of sinh x is cosh x, which is similar to the sine identity, but then differentiating cosh x gives us sinh x. There's no negative here. And finally, d by dx of tanh x is sec squared x, where sec is just 1 over cosh. It's like sec, it's 1 over cos. And then we have cosec x, which is 1 over sinh. And then you guessed it, coth x, which is 1 over tanh. Now we can look at the inverse of these functions. So y equaling sinh to the minus 1 of x. And again, this is not the same as sinh of x to the minus 1. And this is also known as arc sinh of x, like we have arc sine of x. And we can find out what the formula for this is by inverting what we're used to. So x equals a half e to the y minus e to the minus y. So we've basically rearranged our equation to be having x as the subject. And then if we just rearrange this to find y as the subject, we should have our inverse function of sinh to the minus 1. So what we can start with is by timesing across this 2, timesing everything by e to the y, and we should get 2x e to the y equaling e to the 2y minus 1. And this can be rearranged by just taking this across into a quadratic formula where e to the y is our variable, and we can then see that e to the y from the quadratic formula is 2x plus or minus the square root of 4x squared minus 4 all over 2, which is the same as x plus or minus x squared plus 1 to the half. And we take the positive root since e to the y is always positive, so we can get rid of that and make it a plus. And then from here we can just take the natural logarithm and see that y, which equals our sinh to the minus 1 of x, equals natural logarithm of x plus x squared plus 1 to the half. And that's our inverse function. And you have to take my word for it, but we can do a very similar process to find our inverse function of cosh. So cosh to the minus 1 of x equals the natural logarithm of x plus or minus x squared minus 1 to the half for x greater than or equal to 1, or it equals plus or minus natural logarithm of x plus x squared minus 1 to the half. Today we've learnt about logarithms, exponentials and hyperbolic functions. In the next video we'll be discussing limits of functions. So if you want to learn more, join me in the next one. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.